Hello everyone, my name is Pavishka Ratnasuriya. My mentor is Dr. Eduardo Comonares, and we are from Midwestern State University, Texas, Department of Computer Science. Our research is about multi-GPU programming pros and cons, a case study. For talking about our research project, I would like to talk about supercomputers. What is a supercomputer? A supercomputer is a computer with high level of performance compared to a general purpose computer. A general purpose computer is something like our personal laptops, but to get a big picture, like you can think about a supercomputer as a collection of computers that are interconnected with nodes. And on the left hand side, you will see a supercomputer that is available at Texas Advanced Computing Center, and you can see it's very large and it's capable of doing so many things, and one of the use is to perform parallel processing. If you have the knowledge of parallel computing, it's really helpful to take advantages of the powers of supercomputers. So for our research, we access the Maverick 2 supercomputing cluster available at Texas Advanced Computing Center. On the bottom, you will see the differences between serial processing and parallel processing. In a serial processing, let's assume if you have several tasks, so the program execute as like task by task. So it executes first task, then goes to the next task, and so on. But in parallel processing, each task can execute in the same time and get the like execution time very uh, optimized comparing to the serial processing. So that's the one of the advantages of parallel processing, and it is very helpful in parallel computing, and using supercomputing we can achieve that advantage. In this slide, I will talk about a GPU. Like for our research, we are using GPU programming. So GPU stands for Graphic Processing Unit. Initially, GPUs are used for gaming and video processing for high-speed graphics and availability of good visual aids. But later on, it is discovered that using GPU programming, you can shrink large numbers and do computations in within seconds. So GPUs are a part of a supercomputing. The performance is computed using flops called floating point operations per second, and it is powerful in parallel computing. It has the ability to shrink large numbers and compute in seconds. Also, it breaks complex problems into thousands or millions of separate tasks and work them out at once. GPUs are many cores. The number of operations processed is very high due to that nature, and CUDA is a parallel computing platform that let programmers to take the advantage of computing the powers of GPUs. So on the left hand side, this is a GPU available at Mavic 2 supercomputing cluster called GTX 1080 Ti. This is the GPU that I accessed for my research purpose. And in the bottom, you will see the difference between CPU and GPU. CPUs are multi-cores while GPUs are many-cores. So multi-cores means it has only limited amount of cores, maybe from 2 to 8 cores, but GPU has hundreds of cores. So let's assume if you have a task to complete, using CPU, you will split that task into 4 parts, but you can split that task into hundreds of parts using GPUs. So it is very powerful and it has so many advantages of using GPU programming. So that's a basic idea of a GPU and GPU programming. The objective of my project is to write different programs for sequential 1 GPU and 2 GPU versions and see the positive and negative aspects of using multiple GPUs when solving problems with larger data sets. Also, identifying the variations of programs' performances with increase of size of data samples for those three versions. And also, one of the main important thing is achieving the communication to communication parallelism and computation to computation parallelism between GPUs while moving from multi-core to many-core programming. So also, I use C programming for my sequential programming and CUDA in C for GPU programming. So this is a basic objective, and our goal is to see what are the advantages and disadvantages of GPU programming by submitting jobs to the Maverick 2 supercomputing cluster. So before starting on the project, we need to have a good idea about the device that we're going to use and what are the properties that device has. So NVIDIA has a device property program that we can compile in and see what are the properties of the device that we are using. So I use that device property program and to get the properties of the device that I'm using in the cluster. So device name is GeForce GTX 1080 Ti and it has a global memory of 11 nearly 11 GB. So all others are the properties. There are so many properties, but this is some of the important properties like shared memory and number of threads and grid size multiprocessors. This is a basic overview of the device properties of the device that I'm using. I use several softwares. So one is the Visual Studio Code for text editor, and WinSCP is used to connect to the cluster and store files and execute jobs, and PuTTY to compile programs. And also I use TACC Visualization Portal to use the NVIDIA Visual Profiler. So these are the softwares that I used for my project. Compilation commands and execution commands. For compilation commands, GCC is used for my sequential program, which is a C program, and NVCC is used for my CUDA program. So these compilation commands will compile my program, and to execute those commands, I use sbatch command, and sbatch my script file. So for each program I need to have different script file, and that script file will be executed and give my the job script with my output. Talking about problem sizes, I had to use three different sizes, and also each program has three matrices that is computing the task that I'm doing. And the smaller size is 16,384 elements, so each matrix contains that 16,384 elements, and the smaller size is that will be able to fit in a one GPU, and it's really small. But to get a like slight variation of the research, I had to use the small size, and medium size will fit to the size of a one GPU, and each matrix contains 0.5 billions of elements, and large size is the size that go beyond the size of the GPU. Large size is the important data size to examine the difference and the impact of using two GPUs, because this size cannot be fit in a GPU, and it's more than 1 billion of elements, and for three matrices it's more than 3 billions of elements that I'm trying to use. So those are my problem sizes. In order to go from one GPU to two GPU and achieve the parallelism or concurrency between multi GPUs, I had to use several conditions. So first condition is use of non-default streams. Stream is a sequence of operations that execute on the device in order. So if I use default streams, which is stream 0, the program will execute synchronizingly. Synchronizing means if you the first operation had to end up in order to execute the second operation. So if I use non-default streams, uh, the program doesn't program operate asynchronizingly. So CUDA stream T stream, the first line in orange color, will create two streams, and to creation I use CUDA stream create with flags, and inside parentheses use CUDA stream non-blocking, which is which is the keyword for asynchronization. And whenever I create streams and I need to execute the kernel function, which is the GPU function, I had to use which stream I'm using. So in this command I'm using stream 0, which is my first stream, and it's non-default. So using non-default streams, uh, it can be achieved the parallelism that I need to. Also, the second condition is using asynchronization commands for memory copies. So if you don't use asynchronization commands and use synchronization commands, what happened is it will copy the first first memory copy, and until it ended, it won't copy the second memory copy. So in order to avoid that, I had to use asynchronization commands, CUDA memory async. So those two commands can execute at the same time. Whenever the device get the second command, it will start executing no matter the first one has finished or not. And also for the third condition is you need to use host memory involved in data transfer must be pinned memory. So the device has pageable memories. In order to avoid the pageable memory, I had to make the memory pinned memories. Pinned means non-pageable. So CUDA malloc host will do that task for me. So if I implement these three conditions in my 2 GPU program, I can achieve the parallelism and concurrency between communication to communication and computation to computation, and that is very helpful in achieving optimized results in using 2 GPU or multi GPU programs. So going to the visual profilers for large size of 1 GPU implementation. So large size, as I mentioned earlier, the size is exceeding the size of a GPU. So in order to execute that program using 1 GPU, I had to send parts of my program, parts of my data. So this is the visual profiler after executing the 1 GPU implementation for larger size. So looking at this visual profiler, you will see the yellow color boxes, which is the communication to communication or data transfer between host to device or CPU to the GPU, and the blue boxes are the computation. So for matrix addition, these are the blocks will give you the idea about the computation. So since I had to send two different paths, you will see the same thing in two different timings. And also if you look at the timings for the process, it starts less than 1 seconds and end little beyond 4 seconds. So in average it took nearly 4 seconds to perform this 1 GPU implementation program. But if you go to the 2 GPU implementation of the same problem, you will see that we have achieved parallelism. First of all, on the left hand side, you will see 0 GeForce GTX and 1 GeForce GTX. That is the index for my GPUs. I'm using two GPUs, namely GPU 0 and GPU 1. And in the yellow blocks, as I said, memory copy from host to device and device to host, you will see GPU 0 and GPU 1 has been executed in this at the same time. It has been worked parallelly and parallelly, and also the computations, the blue boxes, GPU0 and GPU1, it has achieved the parallelism again. So in this visual profiler, as it sees, the operation started in between 8 seconds and ended at 9 seconds. So it took only 1 second for the total process, comparing to the uh, one GPU. It's very faster and it's very optimized because you can use multiple GPUs running concurrently and achieving more results and very fastly. After after executing and compiling all the programs, I need to analyze the performance. So for performance analysis, we use execution time and speed up. For execution time, which is computed in milliseconds, so for three problem sizes and three versions, you will see when I go to the largest dataset, sequential program took 4532 milliseconds. But from 4532 milliseconds, when I come to the 1 GB implementation, it took only 35 milliseconds. This is for the execution time taken during by the GPU itself. And looking at 2 GPU, it's much faster comparing to the sequential and 1 GPU, because 1 GPU took 35.4 milliseconds, and going to the 2 GPU it took 17.6 milliseconds. So looking at the table, you will see a pattern, because 2 GPU program always takes the fastest time for the certain task. And looking comparing it to the sequential, so using multiple GPUs, I have done like 3 billion. I have worked with more than 3 billions of elements in nearly like 17 milliseconds, comparing to the sequential program of 4500 milliseconds, which is very faster and which is very helpful and advantageous. Execution time curve for 1 GP and 2 GP, because it's nearly same timings, and the difference between each columns, each uh, execution time is like 500 milliseconds. You won't see a much deviation between those two lines, but looking at the sequential line, it has a slight deviation. It's very deviated, and it runs it takes so much time whenever I increase the problem size. Speed up table. Speed up is referred to as the how much faster is your parallel program comparing to the serial program. So if you look at the table, whenever like you increase the problem size for 1 GPU and 2 GPU, speed up keeps to be increasing. But looking at 2 GPU programs, it's almost nearly 2 times faster than 1 GPU program, but it's very faster than comparing to the sequential program. If you look at the largest data sets, like 1 billion of data, you will see its speed up of 2 GPU is 256 times faster than your sequential program, and it's nearly 2 times faster than your 1 GPU implementation. Looking at the speed up curve, sequential doesn't have a speed up because there's no anything to compare with your sequential code, but for 1 GPU and 2 GPU, you will see until it comes to zero point 0.5 billion of data size, the program has a very big deviation, and then from there onwards the deviation has been decreased, but still the speed up is increasing very fastly whenever you increase the problem size. But the figure will show you how much faster still the 2 GPU comparing to 1 GPU. Looking at this curve, it's very fast and it's very optimized, and you can achieve so many advantages using 2 GPU implementation. So after analyzing everything, I came up with the positive impacts of using multiple GPU programming. So first impact is the execution time for a task become more faster than using one GPU in large data sets. Also, two or more GPUs can communicate with each other. So you can communicate between GPU 0 to GPU 1, like send data from GPU 0 to GPU 1, or receive memory copies, so and so many things. That will reduce the time taken for the communication between your CPU to GPU. That is one of the advantages. Also, using multi GPUs can execute parallelly, which optimize performance of the program. As you see above the visual profiler, you can see how the difference between 1 GPU and 2 GPU for large data sets, and how it achieves the parallelism. Also, communication to communication parallelism and computation to computation parallelism can be achieved between GPUs, and that is shown by the visual profiler earlier in the PowerPoint. For negative impacts, CUDA malloc host that will use to allocate memory in the host, which is non-fetchable memory allocation. It took much time for the allocation purpose. And the other negative impact is power and energy for using multiple GPUs relatively higher than the single GPU implementation. So It nearly took like two times the power and energy needed for the one single GPU when using multiple GPUs. Those are the two negative impacts of multiple GPUs that I came up with. And also, we achieved our goal using the during this project, and we see the negative and positive impacts of multi GPU programming, and we are looking forward to work on with complex problems and see how multiple GPUs can be helpful in achieving optimized results. I would like to thank Dr. Magali Winkan and Julie Scales and Jukwa Committee for letting us to work during this summer on our research projects, and special credit goes to Dr. Eduardo Comunaves for uh, teaching students parallel computing and having classes during semesters and giving an idea of new concepts in computer science field, and also Department of Computer Science for having Turing supercomputing cluster, a small Turing cluster in our department, and also Texas Advanced Computing Center for letting us use the TSCC Visualization Profile and Maverick 2 cluster, and also NVIDIA for having NVIDIA tutorials and letting us the ability to do GPU programming and so on. Thank you very much for everyone who listened to my project.